Okay. So first of all, I'd like also to thank the organizers for organizing this very interesting workshop in this unique setting and for giving me the opportunity to speak in front of such an important audience. Um, Today I'm going to propose a novel interpretation of quantum turbulent flows. Namely, I'm going to try to drive some parallels between active turbulence in classical fluid and quantum turbulence in fluid helium. This might seem, and actually it is, to some extent, a very distant topic to what we've heard in the last few days. But I'll try to make some connection with the systems that we have, what we have learned and we have seen in the last few days. So first of all, let me thank the people with whom this research has been possible. So Giorgio Krustolovic from CNRS in Nice, Carlo Borenghi, who is in the audience, and Andrew Bagley from Newcastle University. And here, most of what I'm going to tell you today is described in those couple of papers reported there. So this is the overview of my talk. I'll start with some introduction of what are active fluids. Active fluids are composed by active agents, which are dispersed in a classical viscous fluid. So we're talking about a multi-phase flow system. And the defining property of active matter is that the fluid is driven internally by its own constituencies, by the self-organization of its constituents. So it means that we have self-propelled particles, agents, which transform stored free energy into motion, so into kinetic energy. Example of active fluids are, for example, different type of bacterial suspensions, swarming of sperm cells, monolayer of tissue cells, and artificially propelled particles. I recommend this review if you want to have an overview on all the different systems. So how things work, very briefly, is that you have an active agent, which is there shown in elongated shape, which moves with the velocity, and while it moves, it injects vorticity into the flow, either by n3 dipoles, so you see in red and blue here positive and negative vorticity respectively, and by generating a wake. So here on the right column, you can see some vorticity fields generated by bacteria on top and sperm cells on the bottom, and also the corresponding streamline. So what is active turbulence? So in these active fields, the motion of those fluids, of those agents, create chaotic spatiotemporal flows. But in contrast to classical turbulence, the Reynolds number is very small. It's vanishing small, and this is mainly due to the fact of the size of the active agents. So we have a Reynolds number which are smaller than unity. And another difference with respect to classical turbulence is that you cannot decide the injection scale. So if you do classical turbulence, you know your injection scale is the size of the propeller, the width of the channel. In this case, the injection scale, which is Ki, K is the wave number, depends actually on the self-organization of the agent. So it's not an input of the problem, but it's part of the solution. And importantly, the injection scale is approximately equal to the dissipation scale. So on the top right, you can see that the magenta curve is the injection curve. So it peaks at the same scale of the energy dissipation, which is the blue line, which is negative. And therefore, there are actually, this means that there are no energy cascades are possible, simply because there's no room. There's no scale separation between injection and dissipation. And so the kinetic energy spectrum does not peak at large scales, as in classical turbulence, and there is no Kolmogorov k to the minus 5/3. This, however, so we see here on the right, on the bottom right, we see an example of spectrum of bacteria. So you see that this peaks at intermediate scale. This doesn't mean that you don't have some long-range correlation. They exist, for example, velocity, but they are not self-linear. One important feature of active turbulence and active fluids is the possibility that the hydrodynamic operation might take place. So to do a very brief example of this, we move into the mushroom world, and we know that mushrooms spread themselves in space by ejecting spores. So if we take the ejection velocity of spore, which is about 8 meters per second, the shape, the mass, and we take into account of the drag of the air, a single spore should travel 3 millimeters. Okay, But actually, we see that the spores travel for more than 10 centimeters, and this is because the ejection of the spore from the hat of the mushroom is not synchronous. So you have a few spores that are initially emitted. They create an airflow, which you can see on the right-hand side. And this airflow is then the spores which are ejected after time delay benefit of this airflow and therefore travel without drag distance, which can be even 20 times the distance of a single distance traveled by a single spore. So now let's move to superfluid helium. So superfluid helium, the model that you use to model superfluid helium depends on two parameters. So if you've got the temperature in vertical between T equals 0 and the lambda temperature above which the helium is an ordinary classical fluid, and depends on the scale. So I'm going to show what our model, which works in the blue region, so almost on the whole temperature range and in a range of scales which spans from below and above the average intervortex scale. I'd like to point out here that not in scale, the range of scales, but from the system size H and the vortex core size Xi on the left, there is they can be like 10 orders of magnitude. So we all know that the superfluid helium can be described via the phenomenological two-fluid model elaborated by Thies and Landau. So according to this description, the superfluid helium is an intimate mixture of two compenetrating and inseparable fluid components. So the superfluid related to biosigns and condensation, the normal fluid which are thermal excitation, and with for the temperature range we are interested in, with the normal fluid is constituted mainly by protons, and the important thing is that the mean path of the excitation is smaller than the average intervortex spacing, so the normal component actually can be considered fluid, and so we can use the Navier-Stokes equation. So the superfluid has no entropy, is inviscid, and so it's almost equal to a classical Euler inviscid fluid, while the normal fluid possesses entropy, so it's the only fluid which can transport heat. Viscosity, they are much lower than the viscosity of air and water, and so it's more or less can be described with the Navier-Stokes framework. Importantly, those two components do not talk to each other unless vortices are quantum vortices are nucleated, and this happens when the velocity difference is higher than a certain threshold. If you put the superfluid helium into rotation, or if you do a temperature quench sufficiently fast. Those quantized vortices are topological defects of the superfluids, and they're actually one-dimensional structure. And importantly, the superfluid vorticity is entirely confined to these vortex lines, which can be described as one-dimensional curves in a three-dimensional space. So formally, vorticity is a distribution, a delta distribution centered on the line. And we know that circulation is around those lines is quantized, and so the superfluid velocity depends on the whole configuration of the tangle of the superfluid vortices via the Biot-Savart law, and then by any potential flow dependent on the boundary conditions. Importantly, these quantized vortices are scattering centers for the thermal excitation, which means that there is an exchange of momentum and therefore a force. This is called the mutual friction force, which is proportional to the velocity difference of the two fluids, or equivalently between the difference between the velocity of vortice and the velocity of the normal fluid. Here I would like to pay a tribute to late Giovanni, who passed away recently and who was the first to elaborate the theory of mutual friction in this 1956 paper. So how do we model this mutual friction force? So actually, if we forget for a minute that the confinement of vorticity on those singular lines is due to quantum mechanical restraints, our model is fully classical. So we model this mutual friction force between vortices and the normal fluid as the viscous drag which an infinitely long, thin solid cylinder exerts to a viscous fluid. And this is because the mutual friction force is proportional to the velocity difference as the Stokes drag. Locally, the vortex is a cylinder. The ratio of the discretization of the line to the vortex core is very large, and the Reynolds number is very small. And therefore, we use the matched asymptotic expansion to determine the friction coefficient, and so we end up with balancing the force on the vortices. We end up with the equation of motion of the for the motion of the superfluid. And interestingly, the friction coefficient beta and beta prime are only depend on three non-dimensional parameters, which is always something which you would like normally when you do some modeling. So two parameters depending on the temperature, so the ratio of densities and the ratio between the quantum circulation and the viscosity of the normal fluid and the Reynolds number. So with this modeling of the force, we can then build our fully coupled model. So on one hand, we have to we have to compute the temporal evolution of the tangle of the superfluid vortices. So with which we discretize in a set of points, which can be like 10, 50, or 100,000 points. And we evolve it with the equation of motion, which is derived by balancing the forces. And this is solved self-consistently with an incompressible Navier-Stokes equation suitably modified in order to take into account the mutual friction force, which you see as the integral in red. So what are the results which we obtained? So we wanted to model an experiment which has been performed in the 80s at the Max Planck Institute that until now did not have any real fully explanation. So here the experiments very briefly. You have the superfluid helium is pushed out of a cylinder via driving a piston, and at the orifice you have a large-scale vortex ring which is created, which is made up of thousands of vortex rings, which you can see in red in the cross-section, and embedded in a normal fluid vortex ring. And so what was seen is that those vortices, those structures traveled a very long distance, more than 20 times the radius. They traveled at constant velocity and they remained compact, but more importantly, they were independent of temperature, so friction, because we all know that as temperature increases, the friction also increases, the friction coefficient, so we would expect the vortex structure to decay. And this is in fact what you find if you don't solve a self-consistent model. You find that the distance traveled depends on temperature. The higher the temperature, the smaller the distance traveled. So what we have done is to model this is that we started for initial condition for the superfluid vortex bundle. We created a toroidal vortex bundle of superfluid vortices with an hexagonal regular lattice. Here I want to stress that for computational constraints, the number of vortices, the big radius R and the small radius A of the torus are one order of magnitude smaller compared to experiments, but the ratio between the two radii is the same. And for the normal fluid, when we do simulation at t larger than 0, we use a normal fluid vortex ring with the Gaussian distribution of vorticity and with the same exact overall circulation of the superfluid vortex rings. So if we perform the simulation at t equals 0, there is no normal fluid. So you have a pure Biot-Savart superfluid evolution, and we effectively see that the shape remains compact. The distance traveled is about 15 or 16 radii. It travel at constant velocity. And then we see at the end that there is some development of Kelvin waves and hence Kelvin wave cascades because we are at t equals 0 on the lines. And therefore, at later times, it starts losing coherence, but it travels more than 16 radii. Then here we see the length, which is a proxy of the energy. T equals 0 is the green dots. And you see that, in fact, it remains more or less constant. At the end, it increases because there is the development of the Kelvin wave. If we repeat the simulation with the normal fluid, so at temperature which is more or less 1.9 Kelvin, so what you obtain is that there are some snapshots, and you see that it travels also about 16 or 17 radii, travels at constant velocity, and the velocity is the same as the velocity that the large scale structure travels at t equals 0. And that, I mean, before the Kelvin wave cascades kicks in significantly. And you can see that it remains compact. And actually, the distribution inside the vortex ring of the vorticity is less steep than what you find in classical fluid. And this is also consistent with the experiment. If we look at the length, then we see that, which is the solid line, the blue line, we see that before, I mean, there is this increase in the t equals 0 in the green dots. Simulation, the length is exactly the same, and we see that after tau naught, so which is the lifetime of a single vortex ring, more or less the length overall is. We can do also another experiment, and this other experiment is to start the simulation with the initially quiescent normal fluid, and what we see is that it is the dot dash curve, the blue dot dash curve. We see that initially the length of the energy decreases, but then there is an inversion of the slope. And for at least the first period, the length doesn't decrease. This is because of coupling and hydrodynamic cooperation. So you see that the vortices move, they inject entropy in the fluid, which you can see here, positive and negative vorticity, respectively in green and blue. And you see that close to the vortices, you see this entropy which is injected, but you also can see a wake. So what this means is that there are two things. So the first is that actually the structure, the superfluid vortices, they steer the normal fluid. So the velocity difference between the superfluid vortices and the normal fluid is actually decreased, and therefore the friction is decreased. So you have a drag reduction and a dissipation reduction. But actually, then also what happens is that the wake created by the vortices then creates like an airflow which has been created in the fungal spores. So vortices benefit from the wake created by neighboring vortices, and this can be seen if we do the same simulation. We take 3 different values of the small radius a. So this means that vortices are closer or less closer to each other, and with an initial quiescent normal fluid. And we monitor the dissipation of superfluid kinetic energy, which is the integral of the line of the scalar product of the mutual friction force and the velocity. And we computed the relative dissipation reduction chi, which is the difference between the initial dissipation and the dissipation at time t divided by initial dissipation. So at the beginning, of course, chi is 0, because epsilon is equal to initial value. And then if epsilon reduces, tends to 1. And what we see indeed is that when you reduce the distance between the vortices, the dissipation reduction is faster. Okay, and this is evidence of hydrodynamic operation, which is the same thing which you observe in certain active fluids. And this is not only due to coupling, because if you do a simulation with a single vortex spring, actually in a quiescent normal fluid, actually what you get is that the dissipation increases. So to have a dissipation reduction, what you need is a collective you need to have a collective effect. So you need that vortices benefit from the modification of the common background in which they are inserted, which is typically an active fluid phenomenon. So I come to the conclusions. Time. So first is that we have observed that to have dissipation reduction, you need more than one vortex, and though this means that and that dissipation reduction is more efficient when vortex. So as I've said, this is a typical active fluid phenomenon feature, and it can be found in bacterial suspension, in fungal spores, but also in cyclists in peloton. So when you know that when you have the Tour de France or Giro d'Italia, you know that the cyclists are close to each other, and then they rotate too, because the ones who are in front spend more energy, and the other one benefit of the wake. This is exactly the same. The closer they are, the more benefit the more benefit there is. In fact, there is a slope, a mountain, then the velocity decrease, and there you don't see the peloton, because then the cyclists start say rarefying because they are not able to benefit of the wake. So I would like to stress that actually superfluid helium can be seen a bit like a platform of to create turbulence on demand. Okay, so if you recall Carlos Baringi's talk yesterday, we can have systems where turbulence is quasi-classical. So you have a spectrum which is a Kolmogorov spectrum, and you're also able to observe the dissipation anomaly, which is typical. I mean, it's the 0th law of classical turbulence, and it's observed numerically. We have done it this year, but also in experiments done in Helsinki. Then, in another setting like the one I've described today, you have some you can have some active turbulence features, so drag reduction, hydrodynamic operation, spectra which don't peak at large scales. And then there's also another type of turbulence, which I unfortunately have no time to describe today, that has no classical analog. And in this case, you have a dissipation excess, so in opposite to active turbulence. And this is because fluids, because only the normal fluid can transport heat, the fluids on average flow in opposite direction. And therefore, in this case, you have, for example, a spectra which is steeper than -5. So the last slide, I will try to, this is the effort which trying to make some links between all the topics that have been described in the past few days and this active turbulence vision of quantum fluids. is that, if you look, as far as I understand, if you compute the mean free path of thermal excitation in fermions in the BCS limit, it is smaller than the vortex core. So this means that actually you should see the same hydrodynamic operation also in fermionic systems. And this could enhance the control of vortices and the manipulation of vortices, which has already been to some extent done in a recent paper with Lens in Florence. And I would like to stress that the fermionic system is the perfect system to do this, because on one hand, on superfluid helium, you cannot manipulate single vortices. You have too much. But there is a possibility of hydrodynamic operation. If you take bosons, you can manipulate single vortices, but the mean free path is too large, so it's not fluid, so you cannot see the hydrodynamic operation. Fermionic system could be actually the place where you could see this active turbulence analog. And with this, I really thank you again. Thank you again, the organizers, and